Welcome to the deep dive. Today we're really diving into the core engines of some major blockchains. We're talking consensus mechanisms, Ouroboros, Casper, and Tendermint.
That's right. And look, if you're wanting to get a solid grasp quickly on how these different systems actually agree on things without a boss, well, you're in the right spot.
Exactly. We know wading through technical docs can be, well, a lot.
Absolutely. So we've gone through the technical comparisons, the history, really tried to pull out the essential bits for you. What are the fundamental differences in how these proof-of-stake protocols work? What are the trade-offs?
Think of this as your clear path to understanding the key stuff about Ouroboros, Casper, and Tendermint. Our mission, to break down how they build trust and reach agreement in these decentralized networks, without getting lost in the weeds.
And to really appreciate these systems, it helps to step back and think about the problem they're solving. It's this old challenge in computer science. How do you get a bunch of computers or generals or whatever to agree when some might be faulty or even outright liars? It's called the Byzantine generals problem.
Okay, Byzantine generals. Sounds pretty dramatic. How does that connect to, validating transactions on a blockchain?
It's a perfect analogy, actually. Imagine these generals surrounding a city. They need to decide attack or retreat together, but some might be traitors sending conflicting messages. How do the loyal ones coordinate? That's exactly the problem blockchains face, achieving reliable agreement when you can't fully trust everyone in the network.
Got it. So, high stakes. How did we get from that theoretical problem to actual code running these networks today?
Well, early on, the focus was more on systems that could handle simple failures, like crashes. Think algorithms like Paxos, Raft. They weren't really built for the Byzantine case of the malicious actor.
Like the traders?
Exactly. Then, back in '99, came Practical Byzantine Fault Tolerance, PBFT. It tackled that head-on, but, it mostly stayed in academic circles for a while.
And then Bitcoin happened.
Precisely. Satoshi Nakamoto's big breakthrough with Bitcoin in 2008 wasn't just cryptocurrency. It was showing how you could actually do Byzantine fault tolerance on a massive internet scale. That really kicked things off.
And proof of stake came about because proof of work, Bitcoin's approach, had its own issues, right? Like energy use.
Exactly. People started worrying about the electricity consumption, how fast it could really scale, potential centralization. So researchers looked for alternatives. Proof of stake emerged as a big one. Instead of miners doing computational work, you have validators locking up or staking their own coins as collateral.
And Tendermint was early in that POS game.
Very early. Jae Kwon's work on Tendermint around 2014 was really pioneering. It was one of the first serious attempts to take all that BFT research and apply it directly to a public proof of stake system.
So Tendermint kind of paved the way for others.
You could definitely say that. It tackled some core POS challenges and really spurred development. Things like Casper, Ouroboros. They built on or reacted to those initial ideas, addressing the same fundamental problems in different ways.
Okay, so what are those big shared challenges for proof of stake?
Well, one of the first ones they hit was the nothing at stake problem.
Nothing at stake. That sounds wrong. Isn't the whole point that you have stake on the line?
It does sound weird, yeah. But in the very early naive POS designs, a validator could vote for multiple conflicting chains without risking their staked coins. If block A and block B were competing, why not just sign off on both? No penalty, double the chance of rewards.
I see. So it breaks the consensus because everyone just agrees with everything.
Exactly. It completely undermines the idea of a single, agreed-upon history.
So how do they fix that? That seems like a showstopper.
The big fix was slashing, basically building penalties right into the protocol. If you get caught double signing or breaking the rules in other specific ways, the protocol automatically destroys or slashes some of your staked coins.
Ouch. So there is something at stake now.
A very real something. Vitalik Buterin was a big proponent early on, and Jae Kwon built it deeply into Tendermint.
Makes sense. Financial pain is a good motivator. What's another major headache for PODs?
Another big one is the long-range attack.
Okay, what's that about? Sounds like sniping from a distance.
Kind of. Imagine an attacker wants to rewrite the blockchain's history, but starting from way, way back, maybe weeks or months ago. The tricky part is, validators who were active back then might have since unstaked their coins.
Oh, so they don't have skin in the game anymore for that old period.
Exactly. Once their deposit is unlocked, what stops them from colluding with an attacker to sign off on a fake history from the time they were validators? They could potentially create a whole alternative chain.
That sounds really bad for trust. How do you stop that?
This gets into a key difference between POS and POW. POW has what's called objective security. The real chain is simply the one with the most work put into it. Anyone can verify that. POS is inherently more subjective.
Subjective. That sounds less secure.
Well, they use a model called weak subjectivity to manage it. It means you don't assume the entire history is immutable just by looking at it. Instead, you need a little bit of recent trusted information to get started.
Okay, weak subjectivity. What does that mean in practice? Like if I'm firing up a new node.
It means a few things work together. First, you mainly trust the current set of validators, the ones with stake actively bonded. Second, when validators unstake, their coins are usually locked for a while, a thawing period, maybe weeks or months. This gives the network time to spot any funny business they might try just before leaving.
Like a cooling off period.
Right. Third, the protocol often says you just can't revert blocks older than a certain point, often related to that thawing period. And sometimes systems might even checkpoint the current validator list onto, say, a POW chain as an extra reference point. So you need a recent trusted state to sync up securely, not necessarily trust going all the way back blindly.
So those lockup times for stake are actually a security feature too, not just commitment.
Definitely. Both Casper FFG and Tendermint have mechanisms to lock or freeze stake. And Casper FFG has a specific rule. Once a block is marked finalized, the protocol is designed never to undo it. Timestamps help enforce that.
Understood. So slashing handles bad voting now, weak subjectivity handles the past. What about the risk of just, the rich getting richer and controlling everything? Cartels.
Yeah, cartel formation is a big concern. Any system where money equals power risks, ending up with a few wealthy players colluding. They could censor transactions, mess with governance, that kind of thing.
How do these protocols try and stop that oligopoly risk?
Tendermint's main answer is what they call extra protocol governance. It's basically relying on the community.
So social pressure. Like people notice on Twitter and complain.
Kinda, yeah. The idea is if a cartel starts acting badly, people will see it, discuss it, and then coordinate outside the blockchain rules. Maybe they organize a hard fork to kick the cartel out, or just apply social pressure.
Relies on the community being vigilant and organized then.
It does. Vlad Zamfir's Casper, especially the CBC version, takes a totally different approach. It tries to build in resistance to cartels right into the consensus rules themselves, things like in-consensus censorship-resistant incentives.
Interesting. Directly in the code, not just hoping people notice. Okay, let's pull back a bit. We hear terms like chain-based POS versus BFT-based POS. What's the main difference there?
That's a really useful way to categorize them. Tendermint is definitely BFT-based, Casper CBC is generally seen as chain-based, and Casper FFG is kind of a hybrid borrowing from both.
And that ties into that classic trade-off, the CTAP theorem. Availability, consistency, partition tolerance.
Exactly. The CIP theorem says you can usually only guarantee 2 out of those 3 in a distributed system. Chain-based POS, like Casper CBC or Ouroboros, tends to prioritize availability.
Meaning the network keeps running, even if there's some disagreement.
Right. It might mean the chain temporarily forks, splits into 2 versions while nodes figure things out, but it keeps producing blocks.
Okay. And BFT-based?
BFT-based, like Tendermint, prioritizes consistency. Above all else, they want every node to agree on the exact same state. The trade-off is if there's a major disagreement or too many validators go offline, the whole network might pause, halt block production, to prevent any inconsistency.
Got it. Availability versus consistency, keep going versus always agree. Let's dig into Tendermint first then, since it was so early with BFT for POS.
Sure. So Tendermint back in 2014 was the first really solid take on adapting PBFT for public POS. Key features. It uses a pseudo-random process to pick a leader for each round to propose a block. But for that block to be final, it needs a supermajority, more than 2/3 of all validators, weighted by stake to sign off on it. Sometimes, if the network's laggy or the leader is slow, it might take a couple of rounds of voting to get that agreement. People sometimes call these rounds polkas.
2/3. That's a high bar. That's the consistency part.
That's the consistency part. It means Tendermint can tolerate up to, but not including, 1/3 of the validators being faulty or malicious without messing up the final agreed state.
And you mentioned Tendermint Core has 2 parts.
Right. There's the consensus engine itself, making sure everyone agrees on the transaction order. And then there's the ABCI application blockchain interface.
ABCI. What does that do?
It's super important. It basically separates the consensus part from the actual application logic.
Yeah.
It means you can build your blockchain application, could be anything, a cryptocurrency, a game, whatever, in almost any programming language, and just plug it into Tendermint's consensus engine using this interface. You don't need to rebuild consensus every time.
Ah, makes it modular. Clever. How does the voting actually work each round?
It's a multi-step process. A leader proposes a block. Other validators then pre-vote on it. If they see enough pre-votes, they pre-commit. If they see enough pre-commits, that magic 2/3 number again, they sign the block, and it's officially committed to the chain.
Sounds thorough. Accountable.
Very. Because of these steps, if something goes wrong, like 2 different blocks get finalized at the same height, which shouldn't happen,
No.
you can usually pinpoint exactly which validators broke the rules by signing conflicting messages. Slashing follows.
What if the leader just doesn't propose anything? Goes offline?
Good question. There are built-in timeouts. Validators wait a certain amount of time. If no valid proposal comes from the leader, they basically vote to skip that leader and move to the next round with a new leader.
So it has some time dependency there.
A little bit, yeah. That timeout part makes it weakly synchronous. But once a proposal is out, the voting itself is largely asynchronous. It just needs messages to get through eventually.
But I've heard Tendermint can't stop if too many validators are offline.
That's the critical trade-off, yes. Because it needs more than 2/3 of the voting power to finalize any block. If more than 1/3 of validators just disappear, network partition, coordinated attack, whatever the chain halts, no new blocks get committed.
Wow. So it chooses safety over staying alive.
Absolutely. Safety and finality first. If things get really bad, it might need human intervention, out-of-band coordination to get the network running again.
So Tendermint. Fast finality, strong consistency, very safe,
Yeah.
but potentially can halt.
That's a good summary. And its design definitely influenced others, including the early Casper research. Showing BFT could work for POS was a big step.
Okay, properties glance for Tendermint.
Provably live under reasonable network conditions, tolerates up to 1/3 Byzantine faults, works for public or private chains, finality is almost instant, like 1 to 3 seconds, and it definitely prioritizes consistency. Safety first.
And compared to other stuff out there.
Well, compared to non-BFT systems like Zookeeper, etc., Tendermint handles malicious actors. Unlike Bitcoin or early Ethereum, which were more monolithic, Tendermint's ABCI makes it really flexible for different applications. The Cosmos network is the big example that uses Tendermint for consensus, builds its own POS logic on top with bonded tokens and slashing.
Right, Cosmos. Okay, let's switch gears to Casper. Sounds like there are 2 main flavors.
Yep, Casper isn't just one thing, it's more like a research family. The 2 big branches are Casper the Friendly Finality Gadget, or CFFG, led by Vitalik Buterin.
The Ethereum guy.
Right, and Casper the Friendly Ghost, often called CBC for Correct by Construction, led by Vlad Zamfir.
So FFG and CBC. Let's start with FFG, the Ethereum one. What was its goal?
CFFG was designed primarily as a way to add strong finality onto Ethereum's existing proof-of-work chain. POW doesn't really have true finality. There's always a tiny chance of a reorganization. FFG fixes that.
So it's a hybrid. POW and POS working together.
Exactly. It was designed to be an overlay. Validators stake Ether in a smart contract. They then vote on specific checkpoints in the POW chain, typically blocks that occur every epoch, which was about 50 blocks.
So miners still made the blocks initially?
In the initial design, yes. POW miners proposed blocks as usual. Then the CFFG validators would vote on these checkpoints to finalize them.
How does that voting lead to finality?
It's a 2-step process, basically over 2 epochs. First, a checkpoint needs to get a 2/3 vote from validators to become justified. Then, in the next epoch, if a checkpoint that descends from that justified one also gets a 2/3 vote, the original one becomes finalized.
Justified, then finalized. Takes a bit longer then.
Yeah, about 2 epochs, which worked out to roughly 20 minutes or so on Ethereum. But once finalized, it's considered irreversible by the POS layer.
And if validators try to finalize 2 different chains?
That's a major safety violation. CFFG has slashing rules for that. If you vote to finalize conflicting checkpoints, you lose a big chunk, maybe 1/3 or more, of your staked ETH. People could even submit proof of this to the POW miners and get a reward.
So even a 51% POW attacker couldn't easily undo finalized blocks.
That was the idea. Once CFFG finalizes a checkpoint, the POW history before that is effectively locked in from the POW perspective. Big safety boost.
But did FFG guarantee the chain kept moving? Liveness.
Not entirely on its own, because initially it relied on POW for block proposals. If miners stopped, FFG couldn't make new blocks, just finalize existing ones.
What about incentives? Why would validators play nice?
Well, besides avoiding slashing, there were rewards for voting correctly with the majority. They also introduced penalties, even for things less severe than double voting, to encourage convergence. They called it Slasher 2.0. Though there was some debate, could these penalties make validators too scared to vote if they were unsure, leading to discouragement?
Interesting dilemma. Okay, quick properties for CFFG.
Finality in about 20 minutes. Good consensus safety. Liveness was initially dependent on POW, generally prioritizes availability, letting POW handle block production.
Right. On to the other Casper. The friendly ghost, CBC.
Right, Casper CBC. This is Lad Zamfir's vision. It's a pure proof-of-stake protocol, no POW hybrid. Big focus on formal methods trying to mathematically prove its correctness and specifically designed to resist cartels.
How does it relate to POW concepts?
It adapts a rule called GhostOst, which stands for Greedy Heaviest Observed Subtree. It's a fork choice rule, sometimes used in POW, to decide which chain is the main one when there are temporary splits. CBC applies similar logic, but with POS votes instead of hash power.
So, if FFG added finality, what's CBC's main focus?
CBC, like POW, actually prioritizes availability over immediate consistency. It doesn't have the same kind of deterministic finality as FFG or Tendermint.
So blocks aren't final in the same way.
Not really. Instead, blocks become probabilistically safer the deeper they get in the chain. With the most accumulated votes, the heaviest chain wins. There's always a theoretical chance, though decreasingly small, that an old block could get orphaned if a competing fork suddenly gets more weight. It's eventual consistency.
How do blocks get proposed in CBC? Is there a leader?
No designated leader like Tendermint. Any validator who has staked can propose a block anytime, based on what they've seen. It's more fluid.
And it has this idea of parameterizable safety. What's that?
Yeah, that's unique. Validators can essentially choose their own risk tolerance. They can set parameters based on how much agreement they want to see before considering a block safe enough for their own purposes. It allows flexibility, maybe lower overhead at block creation time.
That sounds like it could handle more validators than Tendermint, maybe, since not everyone needs to agree instantly.
That's one potential advantage, yes. Tendermint's need for a 2/3 supermajority right now to make a block can limit how many validators can efficiently participate.
Yeah.
CBC, without that immediate finality bottleneck, could theoretically scale to a larger validator set more easily.
And the anti-cartel focus is baked in.
That's a core design goal. The economic incentives and consensus rules are meant to make it really hard for even a powerful group of validators to collude effectively to censor or control the network.
Okay, so CBC properties.
High availability allows forks temporarily, aims for safety even if the network is asynchronous, live under partial synchrony, designed to be cartel resistant. Safety level is kind of an estimate based on validator settings and chain depth.
Got it. Two very different takes under the Casper umbrella. Now let's talk Ouroboros. That's Cardano's consensus, right? And there are lots of versions.
That's right. Ouroboros is the family name for the POS protocols Cardano uses. And yes, it's evolved quite a bit. There was classic BFT, then Prouse. Prouse was significant. It introduced stake pools, which helps decentralization by letting smaller holders delegate stake.
Stake pools, okay. What else?
Then Genesis, focusing on letting new participants join securely. Chronos, for better timekeeping across the network. Crypsinus added some privacy features. Hydra is their big layer 2 scaling solution. And the latest refinement for the base layer consensus is often referred to as Ouroboros Peras.
Ouroboros Peras. Let's focus on that one for comparison. What's its approach?
Peras is fundamentally a chain-based POS protocol, like CBC in that sense, but it adds a twist. Weighted voting among the stake pool operators specifically to achieve faster settlement times.
Faster settlement. How fast and how does that work?
It aims for near-instant finality, targeting around 2 minutes. The stake pool operators essentially vote on which chain they see as a valid heaviest one, and this voting helps the network quickly converge and consider recent transactions settled. It's much faster than, say, CFFG's 20 minutes, but achieved differently than Tendermint's instant BFT finality.
Okay, near-instant finality via voting. What about security assumptions? Scalability.
The security rests on the assumption that less than 50% of the total stake is controlled by attackers, similar to PariW's 51% assumption. And that fast settlement is key to its scalability goal. It's designed to work smoothly with Hydra, their layer 2 system, to handle much higher transaction volumes.
So if we line them all up, Ouroboros Peras, Casper FFG, Casper CBC, Tendermint, what are the absolute key differences again?
Okay, quick recap based on the sources. Consensus type, Peras is chain-based with voting. FFG is a hybrid overlay. CBC is pure POS chain-based. Tendermint is BFT-based. Finality, Peras 2 mins, FFT 20 mins, probabilistic. CBC is eventual consistency, no hard finality. Tendermint is instant, 1 to 3 secs.
Security threshold.
Peras assumes 50% malicious stake. Casper relies heavily on slashing economics. Peras focuses on fast settlement integration with Hydra. Casper's depends on the implementation, like Ethereum's upgrades. Tendermint offers high throughput, but might have overhead with huge validator numbers.
Wow, it's really clear there's no single best way. It's all about those trade-offs. Where do you see things going from here, future developments?
Well, honestly, public POS is still pretty young compared to proof of work, which has been running reliably at scale for over a decade. There's still a huge design space to explore.
So lots of room for improvement.
Definitely. For Tendermint, maybe new ways to propose blocks or speeding up those voting rounds, maybe using new crypto to shrink block headers that helps things like Cosmos's IBC protocol, or just optimizing the network layer to handle way more validators.
Enough for the others.
Similar ongoing work. For Casper, maybe refining slashing, improving liveness guarantees for CBC. For Ouroboros, the big thing is rolling out and integrating Hydra for that layer 2 scaling. It's constant evolution.
Constant refinement. Okay, let's try and wrap this up. Key takeaways for listeners from this deep dive.
I'd say Tendermint gives you safety and instant consistency, but risks halting. Casper FFG was a practical way to add finality to Ethereum. Casper CBC goes for a pure POS design focused on safety and cartel resistance, accepting eventual consistency. And Ouroboros Peras targets that sweet spot of fast settlement and scalability.
It really drives home that choosing consensus is about balancing these priorities. Safety, liveness, consistency, speed, depending on what your blockchain needs to do.
Exactly. Hopefully you now have a much clearer picture of the core ideas and differences between these important protocols. You're better equipped to look deeper into the parts that interest you most: security models, scaling, governance, whatever it might be.
All right, and one final thought to leave you with. As this whole field keeps maturing, will we see these different approaches start to merge, maybe adopting the best bits from each other? Or will specific use cases always demand these distinct designs? And what new challenges pop up as these things get bigger and talk to each other more? It's definitely a space to keep watching. Thanks for tuning in to The Deep Dive.